And now finally we reach layer 4, the transport layer. Well, assume you use HTTP, used by all the web services, the web, hypertext transfer protocol, and this typically uses TCP, reliable transport between client and server. That's what's required for HTTP. TCP, as you all know, is a stream-oriented protocol. It's not transaction-oriented. So HTTP, that's rather transaction, but here we have to use TCP because, well, the transaction-oriented TCP, there was one, TTCP, was never successful. So TCP, some characteristics or the key characteristics, TCP is network friendly. TCP uses timeouts. Timeouts, they are important, and as you know, TCP can avoid congestions in the network, can slow down the transmission. So congestion avoidance, it's a key component of TCP. This is why we always want transport layers protocols to be TCP friendly. Well, so what happens before we come to the problems? First of all, we are here a client, you know, three-way handshake. Without any problems, this takes quite long. Assume a GPRS network with a delay of 500 milliseconds. Yeah, that's quite common. Even if you speed this up, 3G, 2G networks, they still have something like at least 100 milliseconds between the mobile station and the base station. LTE networks still, let's say, something like 50 milliseconds. Okay, so the classical networks, they have a problem that all the handshakes, well, it takes some time. Okay, that's not very fast. We'll come back to this example. That's one thing. So these many handshakes, it's a problem if you have higher latencies. That's not the case in fixed networks. You have something like 10 milliseconds, but here can be quite high. What else do we have? So that's kind of first problem, too chatty protocols. The second problem is the congestion control in TCP is based on timeouts. What does it mean? TCP says if I do not get an acknowledgement within time, I assume there was a packet loss due to congestion. Because then the sender cannot send back an acknowledgement. Okay, the problem is in wireless and mobile networks, there can be packet loss due to transmission errors, interference, or that's a wireless problem, or mobility problem, packet loss due to the change of the network. We learned that changing the subnet may cause a packet loss. And this means for TCP, oh, there's congestion, which is completely wrong. What is the reaction of TCP? Congestion, that means I have to slow down transmission, which is fully correct in a situation of congestion, but doesn't make any sense in the case of a transmission error due to interference. Why slowing down? Just continue sending. So what? It was interference. Or if you change the network, why slowing down? Just continue. So it's not a congestion. Now you may remember, this is why we want to have this kind of lossless handover when it, for example, in LTE networks. So TCP performance degrades. That's really a big problem because the assumption of TCP is simply wrong. The point is, the transport protocols, here TCP, usually designed for fixed end systems, for fixed wired networks. So a lot of emphasis was put on performance of TCP, congestion control, congestion avoidance, how to make retransmissions more efficient. The congestion control, that's basically the heart of TCP. TCP friendliness keeps the internet together. So in fixed networks, packet loss, well, the reason is usually overload. Because routers, they have to discard packets as soon as the buffers are full. What else can they do? The outgoing buffers are full, you have to drop packets. And there are many clever schemes which packet to drop, etc. But how can TCP recognize this? TCP is an end-to-end protocol, as we all know. Well, as I said, only indirect via missing acknowledgements. There's no mechanism telling the TCP there's no congestion, everything is fine, please continue. So if I assume congestion is the reason for packet drops, then a retransmission is not a good idea. Because retransmission would simply contribute to the congestion and make them even worse. And this is why we react with slow start algorithm. Well, that's just to repeat, you should know slow start from the computer networks class. The idea is that you have a certain congestion window at the sender, and you start with a certain size of the congestion window equal to 1 segment. And then if you receive acknowledgements, you let this congestion window grow up to a certain threshold, resulting in an exponential growth, and then it continues with a linear increase. If you miss an if there's no acknowledgement, that means you have the current congestion window, that's your new threshold, you drop back to 1 segment size, and then exponential increase, linear increase. That was the idea of TCP, C Computer Network lecture. Okay, that was a slow start algorithm, and what else do we have in TCP? We learned in computer networks that there's fast retransmit, fast recovery. Usually TCP sends an acknowledgement only after receiving a packet. Okay, you receive something, and then you send an acknowledgement. If the sender receives several acknowledgements for the same packet, that means there's a gap in received packets, because we acknowledge only bytes that are received. There's no gap, everything is in correct order. So this is why we have to reorder the receiver, etc. So, but what do we know? As long as we receive acknowledgements, then at least the receiver, okay, got packets up to the first gap, but this is more important, and is actually receiving packets. Great. That's the idea of fast retransmit, fast recovery is, okay, we learn it's not a problem of congestion. It's just, well, it's a packet loss. So do not use slow start. Do not shrink the congestion window, because there's no problem in between. So slow start, fast retransmit, fast recovery, these are standard mechanisms in today's TCP. Please go to the computer network lectures if you do not know these details of TCP. Okay, what happens if we have mobility? Still, TCP assumes congestions if packets are dropped, which is wrong. We know we have quite often transmission errors and mobility. So if you roam from one access point to another one, packets might get lost. You learned that we try to avoid this. Try to avoid. Not always, doesn't work always, but we try to. Forwarding from old phone agent to new one, etc., etc. So performance degradation can be quite extreme, but we cannot change TCP, large base of installation, so we have to stay compatible. Plus the basic mechanisms of TCP keep the internet together. I will just show you one example, a research idea, what we could do. It's called Snooping TCP. What is the idea of this transparent extension of TCP in the foreign agent? So if you send a packet to the mobile host, you buffer them here. You buffer the packets in the foreign agent. That's the idea. And if you lose now packets here on the wireless link, you can retransmit them from the foreign agent. So you do not have to have a retransmission via the whole wired internet. So that's basically the idea. So you perform a local retransmission, and the idea is this is faster compared to the retransmission from the original correspondent host. So the foreign agent therefore snoops the packet flow and recognizes acknowledgements. And that's, oh, okay, there's a problem. I will immediately retransmit. You can also filter acknowledgements. So you have to change the TCP only in the foreign agent. That's the idea. But you still keep the same TCP in the mobile host and in the correspondent host. You just snoop the data flow. So, what does it mean? Data transfer to the mobile host. Foreign agent buffers the data until it receives the acknowledgement. Great. You detect the packet loss. As soon as you see duplicated X or timeouts, you can immediately retransmit. And this is transparent for the fixed network. Perfect. If you have a data transfer from the mobile host, well, the foreign agent also detects packet loss by checking the sequence numbers. And you can immediately answer with a negative acknowledgement to the mobile host, so the mobile host can retransmit the data, and the delay is much shorter compared to a retransmission to the correspondent host. So that's the idea, and you can even further integrate the MAC layer so that the MAC layer detects duplicated packets, etc., discard them, so you can even mix the layers. There are some problems, quite obvious. Well, you don't see this as an implementation. There were some other ideas really isolating the wireless link from the wire link. Here, it's not fully isolated. As soon as you use encryption, you will not see anything. Think of IP security. There's no TCP to snoop. You will not see it. So that's an idea, but doesn't really work. Still, we have the problem of performance degradation. What else can be done? We could use the fast retransmit and fast recovery. How to do that? Well, we know if we change the foreign agent, this may result in packet loss. Maybe the old foreign agent tries to forward packets, but maybe this doesn't work. Well, depending on which kind of network this is, which kind of organization, etc. Maybe complete different companies and you go from a public to a private hotspot, etc. So, well, in the worst case, TCP reacts with the slow star, although we don't have the congestion. We can now use the fast retrans mechanisms by forcing it. The point is, as soon as the mobile host registers with the new foreign agent, the mobile host sends duplicated acknowledgements on purpose. And this actually triggers the fast retransmit mode at the communication partners. So they say, oh no, this was not a loss due to congestion. We get several X, and several X tell me, oh, that's fast retransmission, so do not go into slow start. So that's one of the ideas. So, plus we force our TCP to continue sending with the actual window size. So after registration, we do not go into slow start. We stay with the current window size. So that's quite simple changes, and we really have high performance. But this further mixes IP and TCP is not transparent anymore, but this can be done. So we can tweak TCP a bit and use the mechanisms that are already there. We can use yet another mechanism. We can perform a so-called transmission or timeout freezing. So think of mobile host, you driving with your tablet into a tunnel. So no packet exchange possible, complete disconnection. So TCP will even disconnect after timeout completely. What we can do is we can freeze a TCP connection. Because the MAC layer quite often already notice, oh, the signal gets weaker, and then the MAC layer can inform the TCP layer, well, there will be a loss of connection. TCP immediately stops sending, but now does not assume a congested link. That's the idea. So you can freeze TCP, set the window to 0, it freezes everything, and that's it. So MAC layer can then signal again if we have a nice quality of wireless link, and we can continue. The scheme is completely independent of type of data, but you have to change the TCP on the mobile host, and everything depends on the MAC layer. So also a problem. Every time you read, you have to change an existing protocol. That's a problem. What else can we do? TCP knows selective retransmission, selective acknowledgements. The acknowledgements of TCP, they're quite often commutative. That means I received all the bytes in sequence without a gap up to this certain byte. And you know from computer networks that acknowledgement of n acknowledges the correct and in-sequence receipt of all the bytes up to n-1. It's a byte stream-oriented protocol. But the classical TCP, if you miss a single packet containing certain bytes, quite often the whole packet sequence beginning at the gap had to be retransmitted. That's so-called go back n. Go back to computer networks if you don't know this term. Go back n. This wastes bandwidth, and this is why we learned selective retransmission, and that's our C2018, so it's quite older one. All the TCPs know this, that, well, we can acknowledge single packets, not only in sequence packets, so we can signal basically to the sender gaps. And the sender can now retransmit only the missing packets, so the non-acknowledged parts of the byte stream. So what is missing? Much higher efficiency. In the early days of TCP, go back n was the solution because the devices could not handle this complexity, because you need some buffer management. Maybe very simple devices cannot handle this, but only tiny devices. But today's devices, they can easily use selective retransmission. Okay, so you see, when it comes to layer 4, there are some research ideas, indirect TCP, snooping, mobile TCP. I did not explain indirect and mobile, but the idea was always, how can we more or less separate, split the wireless from the wired links. Some of them really separate them, isolate them, more or less, but they are all problematic when it comes to encryption, when it comes to TCP semantics, etc. So they all have their problem. What can be done, what is quite simple, that's we can use fast retransmission, fast recovery. That's integrated in TCP. So, not really transparent. We have to implement this. The same is true for the timeout freezing. You have to change TCP, and it depends on the MAC layer. We can use selective retransmission. That definitely something you have to do. It's interesting to see that many years ago there was a transaction-oriented TCP, never successful. So, again, a different TCP. So in the end, well, we can tweak here and there, but there's no perfect TCP solution for wireless and mobile links. But we use it. So what can be done? There are some kind of improvements. I told you a bit about some initial research work, indirect Snoop, mobile, transaction, TCP, etc., freezing. But then there was a standard called TCP over 2.5 3G wireless networks, made at a time when the first 3G networks came up, and that's basically kind of a fine-tuning of TCP. What does it mean? Well, TCP has to learn to live with links that sometimes have low data rates, 46 kilobit per second, sometimes higher, but quite often asymmetric. So in one direction, 64, in the other 384 or 5 megabit or whatever. Asymmetry can be factor 10 up to factor 1000. Periodic allocation release of channels, radio channels, very high latency, high jitter, packet loss. Learn to live with it. So, what can be done? There are some suggestions. One is use a large initial sending window. We know TCP usually starts with a sending window, one segment, and then tries to adapt to the available data rate on the link. But here maybe we want to send from the very beginning with a high data rate, so we go for a large initial sending window. Maybe everything is over using this very first window. Use a large maximum transfer unit, use selective acknowledgement, yes, that's what we learned. Use something, it's called ECN, we know from computer networks, explicit congestion notification layer 3 mechanisms. No header compression, but timestamps, that's something special. That were some suggestions. And this was adopted in very first standards for 3G applications, so-called I-mode in Japan, running over, that's 3G, what we call UMTS in Europe. That was adopted as TCP with wireless profile in the wireless application protocol, WAP. It uses some TCP, but with a wireless profile, WAP 2.0. There are some alternative TCPs with different congestion control algorithms. If you're interested in this, in computer networks, we discuss them, TCP Vegas, TCP Reno, etc. So different ways of handling congestion. But what is very, very important is what you see right here. This inequation gives you the maximum data rate you can achieve with TCP. That means this is an upper limit. Well, the real data rate is way lower, but this is at least an upper limit you can show, telling you the maximum data rate is always less or equal to 0.93 times the maximum segment size. It's something you can set, TCP, divided by the round trip time times square root of the loss probability. Now think for a second about this inequation. What is missing? You calculate the data rate, maximum data rate at layer 4 based on maximum segment size. That's something fixed. The round trip time and a loss probability. What can you influence? Okay, you can set a certain maximum segment size. Nice. But what you can really influence is the round trip time and the loss probability. We learned the round trip time of GPRS. Oh, that's really a problem. Loss probability is also high. And this is the motivation why now with the 5G networks, we want to have really, really low latency and also low round trip time. This is one of the motivations. So then we can have higher data rates. So we have to optimize the round trip time, lower and lower and lower. Plus, we have to have a very low loss probability. There's a parameter that's missing here, and that's not an error. Which parameter is missing? Do you see anything about the data rate of the link? No. So by the characteristics of TCP, this doesn't matter. The limit is given by the round trip time and by the loss probability, and not the link. And this means, in the end, well, it's not worth to have faster and faster and faster mobile and wireless networks as long as the round trip time and the loss probabilities are high. Loss probability, okay, that's given by physics, interference, etc. But we have to bring down the round trip time. Otherwise, it doesn't make any sense to have gigabits per second over the layer 2 link if we then use TCP, as long as we have high round trip times. And the reason is quite simple. The round trip time directly influences slow start algorithms. this ramping up of the data rate using TCP. This is influenced by the round trip time. All the timeouts are set there. So that's one of the problems, and some more improvements. One is called performance enhancing proxies. That's a general term of how you can improve performance by placing a device between the internet communication partner and the mobile system. Okay, we saw already we can do something like local retransmissions, local acknowledgements. That was our snooping, indirect, whatever TCP. But we can also help by adding some content filtering, compression, downscaling. So this is rather in the application layer. You can do this on layer 4. You can do this on applications. You can filter certain services. So that's all nice. And that was one of the proposals to do this. It's always a problem. It breaks end-to-end semantics. So think of using IP security. That means this is some kind of man-in-the-middle attack. And in the end, you have to choose. Either you boost the performance by using performance-enhancing proxies. There's a standard for it. Or you really have some kind of end-to-end security. You cannot do both. So that's a problem. There are some more open issues. You have standards for slow links, recommending header compression and no timestamps. You saw the recommendation for 2.5G and 3G said do not use header compression, but use timestamps. Okay. And then there's also an RFC telling you if you have links with errors, do not use this explicit congestion notification. But the other recommendation said use explicit congestion notification. So what happens if you have a slow link with errors? So, okay. There are some different recommendations depending on what type of links you have, and they do not always recommend the same. So there's arguments for one and arguments for the other. You see, there's not a clear picture on layer 4 what you can do. You can tweak here and there, but there's not a clear this is the mobility solution for layer 4. So now, to sum this up, what are the problems of using TCP over wireless links? Why is this a problem? So there was a lot of research going on, but many of these enhancements simply fail or are not widespread. Why? And then there was at least a recommendation what to do. So what can you optimize in wireless links in favor of TCP performance? So what can be done at least?